Let's talk now about solving systems of linear equations, and here we'll be using both the addition and the substitution methods. Now we've seen what we have when you have a single equation of two variables, and that is you have a line. So consider the equation 2x plus 3y equals to 12. All right. Reasonably straightforward. Here we could graph this. All right. And we could graph this by plotting individual points. However, the typical way is to write this in slope-intercept form. So here we can solve for y. Let's subtract 2x from both sides. That gives 3y equals negative 2x plus 12. And now if we divide both sides by 3, we get y equals negative 2/3 x. If you divide 12 by 3, you're just going to get 4. So here we've gone ahead and isolated our y. But now by isolating our y, we can go ahead and graph this. Notice that because this would equal, if we set x equal to 0, this would go away, and we'd have y equals to 4. That means that 0, 4 is a point on our graph, and that would be our y-intercept. So here, let's put in a few numbers here. Just like that. So that would be our y-intercept. And now our slope, negative 2/3, means that from this point, we could go down 1, 2, and then right 1, 2, 3. Right? Down 2, right 3. So we would then form a graph. And now we know that we have some solutions to this graph. Here's a solution, 0, 4. And in fact, we find another solution here by just following the directions that our slope gives us. And that would be, what, 3, 2. But, of course, there are a bunch of other solutions to this equation. And, in fact, here they all are. They're all the points on our graph. Okay? Now, let's consider another linear equation, something totally different, unrelated to this one. Let's say, for example, we have 3x minus 4y is equal to 12. Or something like that. Okay? So now we can go ahead and graph this one. And again, we'll do it the same way. Let's isolate our y, minus 3x, both sides. And that's gone. And this gives us minus 4y equals negative 3x plus 12. And now we can divide on both sides by negative 4. Here, double negative makes that a positive. So we get y equals to positive 3 over 4x. And then 12 divided by negative 4 is negative 3. And so we have another graph. And here, let me go ahead and graph that on the same plot here. So let's see here. Let's use, I'm going to go ahead and use a pencil to graph this one. So we have minus 3 here, which means that if x is equal to 0, y is equal to negative 3. So 0, negative 3 is my y-intercept. 0, negative 3. Now my slope of 3/4 means from here I should go up 1, 2, 3, and then right 1, 2, 3, 4 to find another point on my graph. And in fact, that's the point 4, 0. And you could graph those just like that. Yeah. And you notice that your two equations have two different forms. Now, they might both be linear, but they don't have anything else in common, really. And, of course, that's reflected in the graphs. The two graphs are totally different. But you'll notice that there is one place that they do share something. This point right here is a point that's common to both lines. Now, what point is that? Well, we don't know. It's kind of hard to tell from just the graph. But it is a point that is a solution to both of these equations. This point is simultaneously a solution to this first equation and this second equation. And as such, it is a solution to both equations at the same time. This is called the solution to the system of equations. Anytime you have two linear equations, you'll find that they cross at some point. Well, now you think about that and you say, well, wait a minute, is that always true? Well, no, actually it's not. In fact, if you have two linear equations, there are three possibilities. The three possibilities are either your two lines will cross somewhere. That's the one that we just saw. The two lines will cross somewhere. In which case, your linear equation, your linear equations, your system has one solution. Now, there's another possibility. It's possible that your two linear equations just never cross. It's possible to have parallel lines. Lines that have the same slope would not cross. So here, your system would not have any solutions, because after all, the solution to the system is where they would cross. So here, the system has no solutions. The third possibility, of course, is it's possible that both of the lines are exactly the same. You say, what do you mean they're exactly the same? I mean they overlap. So it's possible that's one of my lines, and the other of my lines is exactly the same one, the one that rests right on top of it. So here these are overlapping lines. Notice that here we have just a single point where they cross. But here they cross at all kinds of points. In fact, they cross at every point along the line. Since they overlap, they share all of their points. Well, in that case, that means that there's no end to the number of solutions you can get. It keeps going forever in both directions. So here, your system would have an infinite number of solutions. Okay, but well, how do I find those? I mean, up here, you had your two equations, and you made your graph, but the graph didn't really tell me where my solution was. I mean, it's kind of hard to tell with a graph, especially when a graph is drawn by hand. It almost looks like I can't really rely on this. Well, it's true, we can't. These illustrations here are just to give you the different cases, to give you the idea as to what could happen. But now let's take a look at how to actually find the solutions to a system of equations. For now, we're going to limit ourselves to linear equations where everything is of power 1. And in a later section, we'll look at things where things are nonlinear. So let's take a look at some examples. First of all, we're going to take a look at examples of this case where the system has one solution. These tend to be a little more specialized. And oddly enough, they tend to be a little bit simpler. So this is the one we'll see the most often. So let's start with this one. Whenever you have a system of equations, there are two different ways that you might go about solving it. So let's consider a system of equations. Let's start off with 5x minus 2y equals negative 2, and 3x plus 4y is equal to 30. Okay? Now this, you'll notice that I put a little brace around it. This brace is here to remind us that these two equations aren't meant to be handled separately, they're meant to be handled together. This notation shows us that we're dealing with a system of equations. Right now we're only dealing with things that have two equations. However, it is possible to have systems with 3 or 4 equations. So of course that bracket would hold all of those together. So the first method that we're going to be looking at is called the addition method. All right. The addition method works like this. We're going to take a look at these two variables, and we're going to look at their coefficients. And what we want to do is we want to multiply either one or maybe both lines by some number so that these coefficients are opposites of another. In other words, one is 5 and one is negative 5, or one is 12 and the other is negative 12. Now, it doesn't have to be these. It could also be these. I want this to be positive 10 and this to be negative 10. I want this to be positive 15 and that to be negative 15. It doesn't matter which one I choose. So here what we're going to do is we're going to choose one variable and multiply the equations so that the coefficient of my chosen variable are opposites. So here, what I want to do is I'm going to take this second one. You say, why did you choose the second one? Why not the first one? Well, again, either one works, but here I'm going to choose this one because if I multiply the top row by 2, that makes that -4 and +4. And that way I only have to do one multiplication. That way I have less work to do. If I chose this one, it would also work, but here I'd have to multiply this top one by 3 and this bottom one by -5. That way I'd have +15 here and -15 there, or something along those lines. I don't want to have to do more work than I have to, so here I will choose this variable and I will multiply the entire top row by 2. Now when I say multiply the entire top row, it's just like with any equation. Whatever you do to one side, you do to the other. So everything's being doubled. So now this equation has been changed to 10x minus 4y equals to -4. This bottom equation, if we had multiplied it by something, it would also change. But here, we realize that's not necessary. Here we can leave that as 3x plus 4y equals to 30. Okay. Now, this is called the addition method because the next step is once you've got these to be opposites, you're going to add the equations together. So here we're just going to go straight up and down. We're going to add. Remember, when you add expressions, you add like terms. X's with X's, Y's with Y's, constants with constants. So here 10x plus 3x will give me 13x. If I add these together, 4y minus 4y is 0. That's the whole point of this. We're trying to get one of our variables to disappear so that our equation is now easier. Notice now if I add these together, 30 plus -4, that's 26. And now things are nice because if I divide both sides by 13, I figured out what x is. So those are gone, and we're left with x equals 26 divided by 13. Oh, in fact, we get a nice number. We get the number 2. Sometimes the numbers won't be so nice. We'll have decimals, fractions, or whatever, but this works out pretty nicely. Now, remember, when we're looking for a solution to a system, we're looking for a point, not a number. Here, we only find the x value. We still need to find the y value. Right? A point is made up of 2 components to our coordinate. Right? 2 coordinates to our point. So we have our x value, but now we need to find our y value. Okay, so now you have found, once you have found one variable, you plug that value into either original equation. Go back to the beginning. You can use either one. It doesn't matter. It's got to be a solution to both, so either one works. Into either equation from the beginning, either original equation, to solve for the remaining variable. All right, so now I know x is equal to 2. I have a couple of equations. I'm going to pick this top one. I just got to pick one. It doesn't matter which one we pick. And I'm going to say 5x minus 2y equals -2. I've taken this top equation, and all I've done is I've said, well, I know x is equal to 2, so let me plug that in. But now notice, this equation now has one variable, just the y. So that's going to be 10 minus 2y equals -2. I could now subtract 10 from both sides. Makes that go away. And I'm left with -2y equals to -12. And then if I divide both sides by a -2, those go away. And I'm left with y equals a -12 over -2. Well, that's a +6. And finally, don't forget, these are not two separate answers. Our last step, let's write our solution as a point. Because remember, that's what you're looking for. You're looking for a point where your equations would cross. Here, these are just numbers. A point on the xy plane is made up of a set of coordinates, the x, comma, the y. And that's our solution. Just like that. Let's see that again. Let's say we have the equation 0.25 x plus 0.04 y equals 0.24. And then the other equation is going to be 15 hundredths, 0.15, minus 12 hundredths, 0.12, is equal to 12 hundredths. Just like that. Now, whenever your equations start off with decimal or fractions as your coefficients, as your numbers, you can work with them exactly the way they are. However, some people feel more comfortable with just whole numbers. This first step that I'm about to show you is entirely optional. You don't have to do this, but if you prefer whole numbers over decimals or fractions, here, notice that all of these are 2 decimal spaces away from being whole numbers. Well, if I just multiply everything times 100, then 0.25x times 100 is just 25x. If I multiply 0.04 times 100, that's just going to give me 4y. And if I multiply 0.25 times 100, that'll just give me 24. Likewise here, I can write this as 15x minus 12y equals to 12. These two equations mean the same thing. They'll have all the same solutions, but this one might be a little simpler for people to work with. So it's up to you. If you want to work with the decimals or the fractions at the beginning, you can. Or if not, you can multiply until you end up with whole numbers. All right? So here I've gone ahead and done that, and now we can continue. So go ahead and give this a try. Go ahead and pause the video, and once you've gotten an answer, go ahead and unpause the video and we'll go through it together. All right, so let's go ahead and take a look at these. I notice that if I multiply this top row by 3, that'll be 12, and that'll be minus 12, and then these will be opposites. Now, I do have a few other options. For example, I could also divide this bottom row by 3, multiply by 1/3. Notice if I multiply that by 1/3, I still get nice whole numbers. So 5, negative 4, and 3. Oh, sorry, 5, negative 3, and 3. So, oh, no, that should be negative 4 and 4. So I could do that. It doesn't really matter which one. All that matters is that we get 2 of our coefficients to be opposites. Here I'm going to pick on these because I realize, oh, this should be easy. But if I wanted to, I could deal with these. I could multiply this whole row by, let's see, 25 and 15 have, that was a common factor of 75. So if I multiply the top row by 3 and the bottom row by 5, well, then those would be opposites as well. So we have a few different options. In fact, here, let me deal with these. Yeah, I could multiply the top row by, no, you know what? Let me just deal with that one. That one should be fine. So let me go ahead and triple the top row. So times 3. The bottom row already has that as a negative 12. I don't want to change that. So let me go ahead and leave this as 25x. Oh, no, that's being tripled. So that's now 75x. 4y times 3 will give me 12y. And here 24 times 3 is going to give me 72. These I'm going to leave alone because I have not multiplied them by anything. Nothing about them needs to change. But now I notice that if I add these 2 rows together, these 2 go away. 75x plus 15x is going to give me 90x. Here, 12y minus 12y, if I add these together, that's going to give me 0, so that all goes away. And here, if we add these, we get 72 plus 12. That's going to give us 84. Oh, well, that's not going to be a very nice number, is it? Oh well, as we mentioned before, sometimes your answers are just not very nice. All right? The answer is whatever the answer is. But here we at least know what our answer is, even if it's not the nicest number in the world. Here I can divide both sides by 90. That part's gone. And I'm left with x is equal to 84 over 90. Now, I should reduce this because I'm not done. I need to plug this in and get the y component of my solution. And the nicer number I have, the easier time I'll have. So if I divide both of these by their common factor, I can divide both of these by 6. That's the biggest number that goes into both. 84 divided by 6 is, hold on, don't tell me, 14. And then 90 divided by 6 is 15. And that'll be a lot easier to work with than this big number here, or than this fraction with big numbers. So there we go. We find our x value. X is equal to 14 over 15. So now we're just about done. We have our x value. Once we have our x value, we can plug that in and find our y value. We're going to go back to our original equations. Now here, this original system and this system, they have the same solutions. They mean exactly the same thing. So here I probably will have an easier time working with this one. I really don't want to have to mix decimals and fractions. So here I'm going to go ahead and multiply these 14 over 15. I'm going to go ahead and plug it into one of my equations. Let me take this one right here. So let's take 15x minus 12y is equal to 12. So I'm going to go ahead and plug that in right here. The reason I chose this one is because I noticed that 15 divided by 15 will cancel out. If I had 25 over 15, that would reduce, but it wouldn't outright cancel out. It wouldn't outright divide, and so I would have a little bit of extra work to do. So here, I choose this one because now that 15 and that 15 will reduce away entirely. They'll divide. So this will leave me 14 minus 12y is equal to 12. Oh, that looks pretty nice. I can go ahead and subtract my 14 from both sides. And that's gone. And then it'll leave me minus 12y equals to negative 2. And finally, if I divide both sides by my negative 12, that goes away. And I'm left with y equals, negative over a negative is a positive, and I can take that 2 over 12 and reduce it to 1 over 6. So that gives me my other coordinate. And now I can put all that together. The solution to my system is, well, let's see, my x has to be 14 over 15, and my y has to be 1 over 6. And there we go. Now, one more example of the addition method. Let's take a look at the following system. So example, let's go ahead and solve the system. And I'll have a system, let's go with 3x minus 4y is equal to 6. And let's have 9x is equal to 12y plus 4. All right, now one thing you might notice about this system is that it looks slightly different from our previous ones. Usually we have x and y on one side, the constant on the other. X and y on one side, the constant on the other. Here, that's true for the first equation, but not for the second one. Well, you know, it's simple enough to just move this over. So before we get started on the system, let's just go ahead and rearrange our equations so that they look like what we're familiar with. So let's write this as 3x minus 4y equals to 6. That was already in the form that I'm used to. But now this one, if I subtract the 12y over this way, I'm left with 9x minus 12y is equal to 4. And that looks a little more familiar. So if ever you have an equation that doesn't start off with things where you have x plus or minus y equals to a number, well, you can always rearrange things until they're like that. All right, so now that we have this system, we can go ahead and solve. I'm going to go ahead and pick one of my variables, and I'm going to go ahead and pick x here. I could pick y, it doesn't really matter. I'm going to go ahead and pick x, and I want to change these equations until these coefficients here are opposites. Well, that's not too bad. The reason I chose this one is because I can see pretty it's pretty apparent that if I just multiply by -3, -3 times 3 is -9. And that'll be the opposite of +9. Okay, so that's what I want. I'm going to multiply that by -3 along the top, and that's just going to give me a new system of equations that looks like, that should be negative 9x. Negative of a negative, that's a positive. Okay, so that's plus 12y. And 6 times -3 is -18. The bottom equation, I haven't changed, so I'm going to leave that the same. And now that I have these matched up, I can go ahead and add the two equations. But notice something strange happens when you add the two equations. -9 plus 9, well, that's 0. Okay, well, that's what we wanted. We were expecting that to go away. But when you add these two, 12y and -12y also add up to 0. So here I have 0 plus 0. Well, that's just 0. But on this side, I have -18 plus 4. That'll give me -14. Notice that all my variables disappeared. But more importantly, once my variables disappeared, they were replaced by a single false statement. This is nonsense. 0 is equal to -14. Here, this is completely false. Whenever that happens, whenever all of your variables disappear and what's left is a false statement, what that means is we were looking for what numbers I could plug into this equation, and at the same time, I could plug into this equation to solve both of them. Here this is saying, no matter what I do, I'm always going to end up with something that's false. I'm never going to end up with both sides being equal. Oh, but the things that make both sides equal, those are my solutions. Oh, okay, so that must mean that this system has no solutions. A system that has no solutions has a name. Any system with no solutions is called an inconsistent system. So here, if the question is find the solutions, the answer is there are no solutions. If the question is what kind of system is this, the answer is it is an inconsistent system. Just like that. Visually, an inconsistent system is this second case. It has no solutions because the two lines are parallel to each other. So whenever you get one of those, that's what's happening here. And in fact, let's go ahead and label this. This would be an inconsistent system. All right, so now let's turn our attention to another method of solving systems of equations. We've seen the addition method 3 times. 2 times it gave us a solution, and 1 time it gave us an inconsistent system. That wasn't the fault of the addition method. That was just, that's the way this equation worked out. But now let's take a look at a few examples of the other method of solving systems of linear equations, and that is called the substitution method. You might be asking, why do I need a second method? Doesn't the addition method work? The answer is, of course it does. Both of these methods work just fine. So you say, okay, so as long as I just learn one, then everything's good. I only need one and I can solve a system. That's true for linear systems. As long as everything's linear, you can use the addition method or the substitution method and everything's fine. However, when your systems are no longer linear, as we'll see in a later section, once you have squares and third powers and square roots and things of that nature, the addition method won't always work. The substitution method will. So you might be saying, well, then shouldn't I just learn the substitution method and let's not worry about the addition method? Well, see, the thing is that when it works, the addition method tends to be faster. So that's why we want to learn both methods. For linear systems, the addition method tends to be faster. Not always, but often. The substitution method is a little slower, but the advantage is that it will continue to work even in later sections when we no longer have linear systems. So here, let's go ahead and take some examples of the substitution method so we can get used to it, and in later sections, it won't be such a new concept. So let's go ahead and just take a system. The example looks exactly the same as it did before. We're going to solve a system. I guess it should be solve the system. And we're going to start off with a nice simple system. Let's take 2x plus y is equal to 2, and 5x plus 3y is equal to 9. Now, of course, we could use the elimination method. And here, if I just multiply the top row by -3, -3y plus 3y would go away. All right, so the addition method does work out quite nicely. But here we want to see it done by a different method. We want to see what the substitution method's about. The substitution method works like this. Step number 1, you're going to pick one of your equations and you're going to solve for one variable. It doesn't matter which equation you pick, top or bottom. It doesn't matter which variable you pick, x or y. That being said, be nice to yourself. If this equation has small, simple numbers, and this equation has big, complicated numbers, relatively speaking anyway, you want to go with this one. And if this equation can be solved for x or for y, well look, y is almost by itself already. I just have to get rid of that 2x. Whereas here, if I wanted to solve for x, I'd have to subtract y and then divide by 2. So be nice to yourself. Pick whichever one requires the least amount of work. In this case, I'm going to go ahead and pick 2x plus y equals to 2. I have smaller numbers. And I will choose to solve for y because that is almost already done anyway. All I just have to do is subtract 2x, and I have y is equal to minus 2x plus 2. This is what we're going to call our substitution. That one. Okay, so now our substitution is going to do what substitutes used to do back in high school, and that's they're going to come in and show us a video, right? Oh, wait, no, that's what I'm doing. Oh, all right. What they're going to do is they're going to substitute in for the normal value. Here, I'm going to take the remaining equation. Now, we just used the first equation to find this substitution. If you plug this back into the first equation, you're going to get, well, you can try it and you'll see what you get. You'll realize that what you get is absolutely true and not very helpful. You go ahead, I'll pause the video and try it and see what you get. Yeah, see, after you simplify, you don't really get anything useful. You get x equals to x, right? Which is true, but doesn't really help us. So here what we want to do is want to plug into the other equation. So once you have found your substitution, plug the substitution into the equation that has, and this is important, the one that has not been used. So here we used this top equation to find our substitution. So now we want to use the bottom equation. All right, so here we go. 5x plus 3y is equal to 9. But here, instead of writing it as a y, I'm going to plug this in. Y is equal to negative 2x plus 2. So instead of 3y, I'll say 3 times negative 2x plus 2. Notice that you now have an equation of just one variable. Here we can distribute the 3. I can get 5x. 3 times negative 2 is negative 6x. 3 times 2 is 6. Hey, those are like terms. 5x minus 6x is negative x. Plus 6 is equal to 9. I could now subtract my 6 from both sides. And that'll get me negative x equals to negative 3. Oh, sorry, that should be negative x is equal to positive 3. I'm getting ahead of myself. Negative x is equal to positive 3. And now I can multiply both sides by a negative 1, because after all, I'm trying to get the x by itself. So now negative of a negative is a positive x. And 3 times negative 1 would give us negative 3. Just like that. And that gives me my coordinate. Now, of course, we want a point. All right? Our solution should not be a single number. It should be a full point, x comma y. So finally, plug the value found into the substitution to find the value of the remaining variable. So here, that's your substitution. Y is equal to negative 2 times x plus 2, but we just found out what x was. So let's do that. Here we're going to take our substitution. Y is equal to negative 2x plus 2. But again, we just found what our x was. So we're going to plug it in right there. And that'll give me negative 3. So that's going to be y equals negative 2 times negative 3 is positive 6, plus 2 will give us positive 8. And there it is. That gives us the solution to our system of equations. X is equal to negative 3 and y is 8. So our solution would be, let's put it here. Our solution to our system is negative 3, comma, positive 8. Now let's take a look at another example of the substitution method. Let's consider the system 5 times x plus y equals 9 plus 2y, and 6y minus 2 equals 10 minus 7x. Now that looks a lot more complicated than the previous examples, but again, if your equation is anything other than just an x and a y, and then on the other side a constant, you can always rearrange things to make them a lot nicer. So here, before I begin solving, I might just want to simplify all this stuff out. Do I have to? No, but it's probably going to make things a lot simpler. Okay. So here, let me go ahead and multiply out this 5xy. So I can write that as 5 times x plus 5 times y. That's equal to 9 plus 2y. And over here, I'm going to leave that alone for right now. 6y minus 2 equals 10 minus 7x. Now from here, I could go ahead and bring my x over this way, move my constant over that way, and same thing for this one. So for this equation, I could subtract my 2y from both sides. Subtract my 2y from both sides, makes that go away. I haven't started solving yet. I'm just simplifying things because my original problem just looked too messy to deal with. So I get 5x. Let's see, 5y minus 2y would give me positive 3y. And since that's gone, I'm just left with the number 9. Right here, I could now add 2 to both sides. Let me do that in red. I could add 2 to both sides, just like that. Makes that go away. And that'll give me 6y is equal to 12 minus 7x. Right. Now, at this point, I'm tempted to now say, okay, now let's add the 7x over this way, because after all, that will put my x's and my y's together. But remember, we're trying to use the substitution method here. And in the substitution method, what you want to do is you want to isolate one variable. So you know what? It might actually be simpler if I just divide by 6, and that will get me my substitution. So here, I'm going to go against what I usually would do, and that's group these together. And that's, let me just divide both sides by 6. And again, whenever you do something to one side, you go all the way across. Right? Proof that math is evil. Right? And so here, we get 5x plus 3y equals to 9. Here, you're left with just the y is equal to, well, let's see, 12 over 6, that's going to give me 2, minus 7x over 6. All right, well, there's our substitution. This one right here is our substitution. So now let's take that and plug it into the y of my other equation. So now I have 5x plus 3 times y. And instead of a y, I'm going to write 2 minus 7x over 6. So 5x plus 3y equals to 9. Let me distribute my 3. there and there. That'll give me 5x plus 3 times 2 is 6 minus 3 times 7x is 21x over 6. And that's equal to 9. Here I can reduce that. 21x over 6, well, that's going to be what? I can divide top and bottom by 3, so that's 7 over 3. I can write that as 5x plus 6 minus 7/3 x is equal to 9. Let's go ahead and subtract the 6 away to the other side. I'm trying to get all my x's together. I'm trying to solve for one variable. So that's going to go away. And I'm left with, well, let's see here. That's 6 taken away from 9 is going to be 3. And if I take 5x minus 7/3 x, we can do that off to the side here. 5 minus 7/3. 5 is like saying 5 over 1. And if I just give these a common denominator, I can write that as 15 over 3 minus 7 over 3, which is going to be 8 over 3. So right here, 5x minus 7/3 x is 8 over 3x. So now we're almost done. We have our x, but we need to get rid of that 8/3. So let's go ahead and multiply by the reciprocal. If you multiply both sides by 3/8, like that. Oh, and I just realized I realized I made a mistake here. When I reduced my fraction, 21 over 6, I divided the top by 3, which gave me 7. I divided the bottom by 3. That should be a 2, not a 3. So that should be 7/2 right there. So my apologies. That's actually going to be not 5 minus 7/3, but 5 minus 7/2. So when I give these a common denominator, that's going to be 5 times 2, that'll be 10 over 2, minus 7 over 2, and that'll give me 3 over 2. So right here, this should be not 8 over 3, but rather just 3 over 2. All right, so that is, well, let's see, I do have whiteout. Just like that. Okay, so that is not 8/3, that is 3/2. All right, there we go. So now, if I multiply both sides by the reciprocal, I'm multiplying both sides by 2/3. I'm going to multiply both sides by 2/3, just like that. And now, let's see here. These will divide away, and that's going to give me just my x all by itself. Here, 2 divides into 2, and 3 divides into 3. And here, 3 divides into 3, leaving me just the number 2. So now that I found the value of x, I can substitute that back into this equation. We can go back into our substitution. After all, we know y, and here I'm just going to rewrite down this equation. Y equals 2 minus 7 over 6 times x. But now we know that x is equal to 2, so we just take that and plug it in right there. So that's going to give me, well, let's see, that's 2 minus 7 times 2 is 14 over 6. I can reduce that fraction, 14 over 6. If I divide the top and the bottom by 2, that'll give me 2 minus 7/3. I can give those a common denominator. I can multiply the top and the bottom by 3, like that. And that'll give me 6 over 3 minus 7 over 3. 6 over 3 minus 7 over 3 will be negative 1 over 3. Oh, but that's what y's got to equal then. So y is equal to negative 1/3. And so putting that all together, the solution to our system is going to be 2 comma negative 1/3. Our last examples for this section come from the third case of what happens when you graph two linear equations. At the very beginning, we saw that if you have a system of linear equations, you can have one solution. We've seen 5 examples of that. You could have no solution, and we saw when that happens. That's an inconsistent system. That's when all your variables disappear, and at the end, you're left with just a nonsensical statement. Something like 2 is equal to 5, or 0 is equal to 4, something along those lines. Finally, let's take a look at an example of what happens when a system has an infinite number of solutions, and how you can tell that that's the case. So let's turn our attention to the example that's given by, let's solve the system. Negative 4x minus 8y is equal to 2. 2x equals 8 minus 4y. Now here, we could solve this by either technique, by either method. We can use the addition method, or we can use the substitution method. It won't matter, because when you have a single solution, you'll get the same solution no matter which technique you use. If you end up with a special case like we're about to see now, you'll end up with the same special case regardless of which technique you use. So here, I'm going to go ahead and proceed with the substitution method. I'm going to say, look, that x is almost by itself anyway. Let me go ahead and use this bottom equation. I'll divide everything by 2, and that'll give me 1x equals 4 minus 2y. And now I'm going to take this, and I'm going to plug it into the other equation. So now, we're going to get minus 4x. Well, that shouldn't be an x. I'm replacing that. So it's going to be minus 4 times x, which I'm about to plug something in for, minus 8y equals to 2. But again, we're not going to treat x as x. We're going to treat it as this substitution. So it's going to be negative 4 times 4 minus 2y minus 8y equals to 2. All right, let me distribute this. Negative 4 times 4, well, that's negative 16. Negative 4 times negative 2y, that's positive 8y, plus 8y is equal to 2. Oh, no, I'm sorry, that should be a minus, shouldn't it? That should be minus 8. So now here, even though we use the substitution method, we still arrive to a familiar conclusion. Notice that these two subtract away, and you're left with a nonsensical statement. So left with negative 16 is equal to 2. So all of your variables disappeared, and you're left with a false statement. Notice we saw that in a previous example. When all of your variables disappear, before we used the addition method, now we're using the substitution method, but in the end, we have the same kind of results. All variables disappear, and you end up with a false statement. Whenever that happens, we end up with an inconsistent system. This will have no solutions. The same thing is true if you have the last case, where you have an infinite number of solutions. It won't matter if we use the substitution method or if we use the elimination method. You'll still get the same kind of result at the end. So let's consider negative 4 x minus 8y equals to 2, and 2x equals to, oh wait, that's the one I just did. I'm looking at the wrong example. Let's take a look at let's solve 2y equals 6 minus 4x, and 8x equals 12 minus 4y. Here, it won't matter if we use elimination or substitution. You'll get the same kind of answer. So here, I'm just going to choose to use substitution. I'm going to go ahead and take this top row and divide everything by 2 because, well, that's a small, simple number to work with. So here, if I divide both sides by 2, I get y equals 3 minus 2x. Divide everything by 2 all the way across, and this is my substitution. If I now take that substitution and plug it into the remaining equation, that gives me 8x equals to 12 minus 4. So I've taken this equation down here. And now instead of a y, I'm going to replace it with a 3 minus a 2x. But now, if I simplify this, we get 8x equals 12. This is going to distribute. Negative 4 times 3 is negative 12. Negative 4 times negative 2x will give me positive 8x. And here I notice these simplify. I'm left with, well, 12 minus 12 is going to give me 0. Okay, so that goes away. And so I'm left with 8x equals 8x. Now, of course, I know I want all my x's on one side. So let me go ahead and subtract this over this way. 8x minus 8x, like that. But when I do that, it also makes this become 0. So in the end, we end up with this result. Just like before, all of our variables disappeared. But whenever all your variables disappear and you get a false statement, that means your system has no solutions. Here, all your variables disappeared and you ended up with a true statement. That's going to be different. That is not a inconsistent system. This is called a dependent system. When all variables disappear and we're left with a true statement, this is called a dependent system. What that means is if you were to graph these two equations, they would be the same line. They would overlap. Now you might say, okay, well then that just means that my answer is infinite solutions and that's it, I'm done. Well, not quite. Because look at this picture. Yeah, the two lines overlap, which means you have an infinite number of solutions. Okay, so why don't I just write that, infinite number of solutions? Well, because we can be a lot more specific. Because notice, I have an infinite number of solutions, but that doesn't mean every point on the plane is a solution. Look, there's a point that's not a solution, and there's another point, and there's another point. There's lots of points that aren't solutions. So if I say I have an infinite number of solutions, that's not really specific enough. What I want to do is I want to say, okay, I have an infinite number of solutions, and here they are. I want to be able to describe them. So here's how we're going to do that. Whenever we have a infinite number of solutions, if you have a dependent system, here's how you want to do this. You're going to go ahead and take your substitution. All right? It doesn't matter if you solve for x or solve for y, but usually solving for y is typical. It's pretty customary. And what you're going to do is you're going to write your equations as your solutions to your equations as a set of points that follow this pattern. So let's go ahead and write this out. The solutions to a dependent system are written by, okay, so we're going to have a few steps. First of all, you're going to pick one equation and solve for y. If you use the substitution method, there's a good chance you've already done that. In this case, I already have. If, on the other hand, if I had solved for x for my substitution, well, I'd have to go and solve for y instead. Right? So pick one equation and solve for y. It doesn't matter which one, because since these are dependent equations, that means they overlap. So they both have the same result. They both have the same equation. If you solve for y on this equation, it will look exactly the same. So now, what you want to do is you want to write your answer as a set of points. Now remember, when you have a set, they look like this. You use the curling braces. All right, so I have a set of points. All right, which ones? How am I going to list them? Well, I can't list them because there's too many of them. So what I have to do is, instead of listing them, I have to describe them. So the way we're going to do this is we're going to write it as a point x, comma, y, where y is equal to 3 minus 2x. Now we could actually simplify that just a little bit further. If we're saying, well, we want points that look like x comma y, where y is equal to that, well, couldn't I just put that in there? So this is one way to write it. However, and I believe this is the way this book recommends, we can write our answer like this. So it's still a set of points, but now our points are going to be x, comma, and instead of writing it as a y, well, we know that's what y is going to equal every time. So it's going to be the set of points x, comma, 3 minus 2x, like that. And this is saying, as long as you give me some x, it doesn't matter what number it is. Here, this is for any real number x. For any real number x. If you give me some number, let's say, for example, 3. Okay, well, I could plug in the number 3 there, and that would give me an x and a y, which is one of the points on this set of solutions. If I give you another x value, let's say -7, I could plug in -7 there and -7 there, and that would give me another point. And that other point would be a point on this system of solutions. All right? So this is what will happen anytime, whether you're using substitution or addition, if in the end all variables disappear and you end up with a true statement. Incidentally, this kind of solution, this is called a general solution because you don't find any specific ones. You find the general pattern that says, as long as a point has that pattern, that is sufficient to tell me that that's a solution. So here these are called this is called the general solution of a dependent system. And you only use these whenever you have a dependent system. All right? So that's the end of the section, and I hope you all have a nice day.